I think we'll begin. There are a few more terms that we have to define. Okay. After that, we are ready for working out some problems. So, the couple of things that we are going to define very clearly is impedance in the transmission line when excited with AC, and we are also going to define a term that we have not seen before in the DC excitation, which is standing wave ratio or voltage standing wave ratio, the significance of these two terms. So, I will begin with the general solutions to the voltage in a transmission line. So, we had V is equal to V plus e to the minus gamma z plus V minus e to the plus gamma z. The first term will be the forward voltage and the second term is the backward voltage. Right. So, I am just writing down the general solution for the current in the transmission line. That is going to be I plus e to the minus gamma z minus just to plus I minus e to the plus gamma z. So, the first thing that we can do is we can use the telegrapher's equation to arrive at an expression for the impedance in the transmission line. So, we need a ratio of V to I. Okay. So, we can always do d by dz of V, right. So, I can write down the expression for V, V plus e to the minus gamma z plus V to the V minus e to the plus gamma z. So, this is the left hand side of the first telegrapher's equation dV by dz. Okay. On the right hand side, we will have, in this case, since we have written gamma, that means that we are assuming that R and G are going to be non-zero and present. We are writing the most general case over here. So, we will have minus R plus j omega L, okay, multiplied by I plus e to the minus gamma z plus I minus e to the plus gamma z. These are the general solutions that we have obtained before, and we are substituting back into the first telegrapher's equation. And then one can go ahead, differentiate the left hand side and take the terms on the right hand side. And the first thing one can do is separate the forward and the backward parts. Okay. Okay. Separate the forward and the backward parts on left hand side and right hand side, and equate them. All right. So, all we are doing is we are going to separate the forward, the backward part on both the left and the right hand side, and we are going to equate them. The idea is to find some relationship between the forward voltage, forward current, right, backward voltage and backward current, and in that process we will be able to find out what the impedance is going to look like, right. So, for the forward part, if I take d by dz of V plus e to the minus gamma z, that is the forward part. So, I am going to take this term and then equate it on the right hand side to the forward term I plus e to the minus gamma z with its coefficients. Okay. So, if I take the derivative, I will have minus gamma V plus e to the minus gamma z. So, I am just using forward term now. Okay. Minus gamma V plus e to the minus gamma z. Okay. It is going to be equal to, on the right hand side I have minus R plus j omega L times I plus e to the minus gamma z. Okay. And from here, the quantity that we are interested is V plus divided by I plus. So, we bring that to the left hand side. All the other terms are brought to the left hand side, all the other terms are brought to the right hand side. So, we can write this down as R plus j omega L divided by gamma. Now, the way we have defined gamma in our wave equation to apply this general solution is gamma is going to be square root of r plus j omega l times g plus j omega c. So, just going to substitute for gamma as r plus j omega l times g plus j omega c under square root. So, I will have this. Okay. So, in other words, the left hand side has to correspond to the impedance in the transmission line, all right. So, this is the characteristic impedance of the transmission line, all right. So, you can mark this as some Z0 or ZC depending upon the convention that you are following, right. Z0 we will use it to represent the characteristic impedance, right, is going to be equal to square root of r plus j omega l divided by g plus j omega c. Okay. It is going to be in ohms. Another way of remembering this is by using series impedance in your circuit model divided by the parallel admittance in the circuit model. In the series we had R and L connected, so we can have series impedance divided by parallel admittance G plus j omega c. Okay. This is your characteristic impedance Z0. Okay. Since we have equated the forward terms, let us also go ahead and equate the backward terms and try to see what we are getting, all right. So, we go ahead. Okay. So, when we equate the backward terms, the left hand side I am having gamma V minus e to the plus gamma z, all right, and on the right hand side I have minus r plus j omega l I minus e to the plus gamma z. Okay. And the quantity that we are interested in is V minus divided by I minus. This ratio has to be equal to the characteristic impedance again, all right, but we notice that in the numerator we have minus r plus j omega l divided by gamma. Once again, gamma is going to be equal to square root of r plus j omega l times g plus j omega c, which means that the ratio will look like negative square root of r plus j omega l divided by g plus j omega c. Okay. Now, one has to realize that we have still found the characteristic impedance, but the negative term appears over there, all right. It should not be mistaken for some active circuit which is providing a negative impedance of some kind. It just signifies that the energy is travelling backward, all right. So, characteristic impedance negative, all right, is occurring because you are taking the backward voltage divided by the backward current. Okay. However, the characteristic impedance as we conventionally denote in all the problems that we will be solving will be having only positive values, but you should be aware that if you are measuring backward voltage divided by backward current, it is not unusual to get negative characteristic impedance, because you have to get signifies the direction of energy transfer. Okay. Now, once that definition is clear, okay, then we can go for the derivation of this standing wave ratio. Okay. For this, we will draw the transmission line model with a slight change compared to what we had done before, all right. So, I will start with the source voltage, which is an alternating source. Right. So, I am having a Vs. The series impedance of this source is denoted by Z suffix s. Following that, I am having a transmission line section. Okay. So, I am going to mark this transmission line section like so, and a load impedance that is connected on the other end, which is denoted by Z suffix L. In order to say that this is a transmission line, we provide some parameters in the circuit diagram. We say that the propagation constant is gamma, characteristic impedance is Z naught. Okay. We also want to mention something about the length of the transmission line. So, to denote that very clearly, we take a coordinate axis, we say that Z equal to 0 and Z equal to L. Previously, we had taken a different coordinate system where the load side was 0 and the left side was minus L. I just wanted to show that you can also use any other coordinate system, alright, which is as long as you are consistent, you will be ending up with the same result. Sometimes I found that the students find this coordinate system easier while going from left to right, it is going from 0 to L. Okay. So, if you feel this to be comfortable, you can stick to this coordinate system for the rest of the course and just base all your derivations on this coordinate system, you will hit no problems. Okay. And to just instill that confidence, I just want to reverse the coordinate system as just not in the textbook. Textbook usually uses the other coordinate system. Okay. So, I am having a current that is supplied by the source, right, since this is a closed circuit. I am going to also mark some values in this circuit diagram. Just going to say that the voltage at the source end of the transmission line, that is the left hand side end, which is Z equal to 0, is V at Z equal to 0, and I am going to denote that with V naught. Okay. So, V naught is going to be the voltage at Z equal to 0. Okay. The voltage on the load end of the transmission line is going to be V suffix L. Okay. On top of that, to be little bit more precise, you can also say that by looking into the transmission line from the source side, okay, while you are looking into the transmission line from the source side, the impedance that you will measure is Z in. It is an effect of the characteristic impedance and the load impedance put together, all right, and we will find out about all these things in just a minute. Okay. So, this is the circuit diagram based on which we are going to start the derivation for reflection coefficient and voltage standing wave ratio. Okay. So, we will begin by writing down the expressions for voltage and current. So, we will start with the transmission line section. Okay. So, in the transmission line section, at any position Z, the voltage is given by V naught plus e to the minus gamma Z plus V naught minus e to the plus gamma Z. This is the general solution to the transmission line equations that we have seen before, right. The current, okay, I of Z is going to look like V naught plus divided by Z naught. Okay. Just applying Ohm's law to get what is the value of I naught plus over here, all right. We have already seen that the characteristic impedance Z naught is going to be V naught plus divided by I naught plus. So, I am just using V naught plus divided by Z naught, and it is a forward term. So, I am just marking it with E naught e to the power of minus gamma Z. And we also know that for the second term, I will have a negative sign over here because Z naught turned out to be negative for the backward propagating case. So, to mark that clearly, I am just putting V naught minus divided by Z naught e to the plus gamma Z. Okay. So, along with the convention that we are using, the voltage at Z equal to 0, I am marking it as V naught, and the current at Z equal to 0, marking it as I naught. Okay. Okay. So, now I will number these equations as 1 and 2. Okay. Now, I will have the sum of equations 1 and 2, all right, along with the condition that I am going to look at z equal to 0, which is the source side. So, I am going to add 1 and 2. People may be confused, why are we adding voltage and current? How can you add voltage and current? Simple answer to that is I will be bringing the value, the denominator z naught to the left hand side, then they become dimensionally stable and you can add the two equations. Okay. Okay. So, I am adding equations 1 and 2, but I am not adding voltage and current. I am just bringing the impedance from the denominator to the numerator, making it dimensionally stable, and then I am adding. Okay. So, this means that I will be having V naught, okay, V at z equal to 0. So, that becomes V naught, all right. On the right hand side, first I will write down the equations as they are: 1 at z equal to 0, 2 at z equal to 0, then I will add them, it is an in between step. So, V of z, all right, z equal to 0 becomes V naught, okay, is equal to V naught plus, once again the exponential e to the minus gamma z, z is equal to 0. So, this exponential is equal to 1, all right. So, that exponential does not fare in this simplified expression, plus V naught minus, this will become the reduced form of 1 at z equal to 0, and then I will be having I naught z naught, okay, is equal to V naught plus minus V naught minus, and I am just going to take the sum of these two. Okay. So, I am going to have V naught plus I naught z naught is equal to 2 times V naught plus. Okay, which implies that my forward travelling wave on the source side is going to be half of V naught plus I naught z naught. Just a rearrangement. The forward travelling wave at position z equal to 0 is going to look like half of V naught plus I naught z naught. Okay. And in order to find V naught minus, you can take the equation number 1 and subtract 2 from it. So, 1 minus 2 can be done, and there you will be ending up with what is V naught minus. It is going to look like half V naught minus I naught z naught. Okay. 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 On the source side, this is how one will write down what is the forward and what is the backward. There can always be some questions as to what is exactly V naught, all right. So, if you look at the circuit diagram, one has to be a little careful. The way we had done bounce diagrams for the DC case, just to understand what is the time based evolution of voltage, we started with an example where we did not have this series resistance in that particular example. So, whatever voltage was applied was appearing as V naught, and then you were calculating the bounce diagram. Now, after that example we have progressed a lot more, all right. We know that if you are looking into the transmission line from the source side, there is going to be an impedance of Zn, all right. So, V naught, if we want to calculate, we have to take the source voltage, all right, and we have to do a voltage division rule between the series impedance Zs and Zn, okay, and then you will have to figure out what is V naught plus, and then you will have to figure out what is V naught minus, and then you have to start drawing bounce diagrams. Okay. So, to be clear, the V naught is coming because of voltage division between the series impedance and the input impedance seen over here. Okay. So, the first step you will do is assume this transmission line entire thing up to the load being represented as a single lumped parameter whose value is Zn. Then you will calculate V naught, and then you will determine what is V naught plus and V naught minus. Okay. That is what this so far it means. Okay. So, at the source side, it is clear what we are doing. Okay. At the load side, okay, we can use V suffix L. Okay. This is nothing but V at Z equal to L, and I suffix L is nothing but I at Z equal to L. Okay. I am writing this down again and again simply because I am using a different coordinate system compared to before. So, just to sync that in the mind, right. IL and VL, I mean that it is Z equal to L, all right. So, we can always write down at these positions, right, what my V naught plus and V naught minus would look like. So, we can say that V naught plus can also be written in terms of VL and IL. So, I can take the equation that I got for V naught plus, okay. So, I can write this down as half VL plus Z naught IL, okay, multiplied by e to the gamma L. Okay. That is simply because the voltage on the load side and the voltage at the source side have a difference in the form of an exponential to the power, exponential gamma L. Okay. So, all we are doing is we are writing down V naught plus in terms of VL, IL. The only change that you will do to your expression is you will account for the propagation loss and the phase constant of your transmission line, the form of e to the power gamma L. Okay. Similarly, you can write down V naught minus as half VL minus Z naught IL e to the minus gamma L. Okay. You can also mark these equations as 3 and 4, they give you the exact same information, means that the unknown quantity is on the left side, you are trying to find out V naught plus and V naught minus. If you know some quantities on the right hand side, all right, if you know VL, IL, and if you know the length of the transmission line, the propagation constant gamma, then you will be able to find out what is exactly the voltage that was traveling forward at the source side, what is the voltage that was going backward at the source side, etc. Okay. It just gives you additional forms of finding the same unknowns. Okay. During the quiz, you may not need to memorize all of this. Okay. If the formula is required, it may actually be given, so that you do not have to worry about memorizing this, you can worry about the application of what you are doing rather than just memorizing all these things. I know that sometimes it can become overwhelming, so you do not have to worry about it. If the question needs something that you need to remember, it will be provided in the questions. Okay. So, another thing is we have marked Z in our transmission line. Now, the way we have marked Z in our transmission line is it is going to be a ratio of voltage divided by current, okay, and it is going to be at the input side or the source side. Okay. At the source side, the voltage is going to look like V naught, which is sum of forward and a backward voltage at that place. Okay. So, it is V at Z equal to 0. Okay. It has a sum of a forward and a backward, which is denoted by V naught plus V naught minus, divided by V naught plus minus V naught minus. This is what is your source input impedance from the source side for a transmission line that is terminated with the load impedance of ZL. However, one can also make this a little bit more elaborate. Okay. From equations 3 and 4, okay, we are able to see that given the load side parameters, okay, only the load side parameters will be voltage at the load, current passing through your load impedance, length of the transmission line and some propagation constant, you will be able to estimate what is the forward voltage that was launched on the source side. Okay. So, using load side parameters you are able to estimate this. Same way, using the load side parameters you are able to estimate what is the backward voltage reaching at the source side. Okay. So, you may very well make use of this information, all right, and plug it into the expression for the Z in, and that will make it look a little bit tedious, that is all. So, V naught plus V naught minus divided by V naught plus minus V naught minus. So, you can always express this in terms of load side parameters. So, which will mean that you will make use of equations 3 and 4, okay, and you will substitute for them here, and then you will arrive at an elaborate expression. I will write the expression directly because there is no magic in the in between steps, okay. So, you will end up getting, since we are dealing with gamma to be a complex propagation constant, it has a real and an imaginary part, okay. So, when you take the exponentials, you take the sum, you take the difference, you will end up with having hyperbolic quantities instead of say sine, or you will be having sine h. Instead of cosine, you will be having cos h. Instead of tan, you will be having tan h. That makes it a little bit more, elaborate, that is it. So, z naught tan h gamma l divided by z naught plus z l okay. Okay. The reason this was done is previous lectures we have seen what Zn would be in the case of a lossless transmission line. In the case of lossless transmission line, we had a very similar expression. We just had Z naught multiplied by ZL plus Z naught tan beta L, all right, divided by Z naught plus ZL tan beta L again, all right. So, this is the expression that we had for the lossless case. I just wanted to make sure that you had it for the lossy case also. And if you remember this, you can always substitute gamma to be, alpha to be equal to 0, and then the sanity check can be whether you get back the same expression. It appears that you will get back the same expression, okay. Now, there are a few more definitions that we will see once again with the AC excitation, right. The voltage reflection coefficient, okay. We can start with gamma at the load end, okay. It is going to be your backward voltage divided by your forward voltage, as we had seen in the prior lectures. So, we are going to write down the exact same thing. So, backward voltage is going to be V naught minus e to the gamma L. Note that everything I am writing in terms of V naught and some parameter, okay. That is how we are denoting everything, divided by V naught plus e to the minus gamma L, okay. So, the way of representing your load reflection coefficient is now V naught minus e to the gamma L divided by V naught plus e to the minus gamma L. One could also go one step further and say that V naught minus divided by V naught plus is your reflection coefficient at the source side, and then if you multiply that with another quantity e to the 2 gamma L, you will be ending up with a reflection coefficient on the load side. This just now gives you a relationship between reflection coefficient at different places. If you know the source side reflection coefficient and the length of your transmission line and say the propagation constant, you can estimate what the reflection coefficient at the load side is going to be, all right, and vice versa, that is all. Okay. The expression that we are already aware of is, we cannot remember all this, right. We can always say that we do know that it is going to be ZL minus Z naught divided by ZL plus Z naught. This we are already aware of from the previous lectures. You are free to use this to find out the load reflection coefficient. If you know ZL, Z naught, you will be able to find out what is going on with your load reflection coefficient. Now, one of the things that we need to now understand is that you could calculate in the bounce diagrams the reflection coefficient on the load side, okay, and then the reflected wave will come to the source side, you will calculate another reflection coefficient, and then you will start marking the bounce diagrams again. That is how we drew the bounce diagrams in the prior classes, which means that the reflection coefficient is a function of position. It is a quantity that changes continuously along the position of the transmission line. That means that gamma can exist anywhere in the transmission line, and every section of the transmission line can have its own reflection coefficient. That is what it means, alright. So, in general you can write down the reflection coefficient gamma to be a function of position z, alright, and you can always take hint from this expression over here, right, and then write down that in general it is going to be V naught minus e to the gamma z, where z is the position coordinate that you have chosen, okay, divided by V naught plus e to the minus gamma z, that is equal to V naught minus divided by V naught plus e to the 2 gamma z. If z is equal to 0, in our case the way we have defined now, it corresponds to the source side, you will end up getting V naught minus divided by V naught plus. So, it is correct. If z is equal to L, you will end up getting what we have got here, alright. So, it is correct. So, at any position z, you can have a reflection coefficient, okay. Now, this reflection coefficient in the case of AC excitation also means that you will be having the superposition of the forward and a backward wave, and some instants of time you will be having the amplitude of the voltage going higher than the forward, alright, and the currents could be higher than the forward current, etc. Which means that we also saw from our simulations that there were some places where the voltage was pegged at 0 and some other places where it exhibited standing wave characteristics, like it was increasing with respect to time, but then going back. So, if you go back to your simulations and use a sinusoid, you say open circuit or a short circuit boundary condition, you will be able to see some standing wave patterns. There will be some nodes, some places which are anti-nodes, and you will be able to see what is happening. So, this means that at certain places the voltage is always pegged at 0, okay. Now, let us look at the other place where it is going between a maximum and some minimum, alright. So, in the case of our simulations, we used only two types of boundary conditions, short circuit or open circuit. In both these cases, the backward voltage went, the superposition of the forward and the backward went to 0 at some instants of time, okay, not at the places where it is nodes, but in the anti-nodes with respect to time, the voltage was increasing and then it was going to 0 and then it was increasing again, it was going to 0, etc. So, that means that there was a maximum voltage in the transmission line and there was also a minimum voltage in the transmission line, barring your anti-node places, okay. So, since we had only two boundary conditions, okay, it will be tough to imagine this, but you could always have terminations with different values of load impedances, okay. In these cases, the reflection coefficients would be different, alright, it would be different. In our cases, for the ideal simulations that we have done, the reflection coefficient was either +1 or -1, okay, but here it means that you can have a fraction, alright, and it could also have a phase associated with it. So, it becomes a little bit more complicated, alright. So, nevertheless, you will end up having, say, a maximum voltage in your transmission line, and you will also be having some minimum voltage in the transmission line that could be non-zero, okay. It need not be 0, 0 happens only because the forward and the backward voltage are exactly equal and they cancel off each other at specific points. But we know that the reflection coefficient need not be plus or minus 1. So, the backward voltage need not be equal to the forward voltage. You can end up with some residual voltage, okay. So, V max divided by V min in these cases is known as the voltage standing wave ratio. Okay, and V max divided by V min, alright, can be simply written as 1 plus mod gamma L divided by 1 minus mod gamma L. The V max depends on the reflection coefficient, alright, and the time it will be maximum, you want to have the positive component coming from the backward voltage and adding up to your forward voltage. That will be the maximum voltage. Minimum depends upon the difference between the two. So, you will be having 1 minus mod gamma L. This ratio is referred to as a voltage standing wave ratio, and it is important in ascertaining the kinds of terminations your transmission line is having. In our case previously we had seen that we were having open and short circuit for the simulations. Okay. So, gamma L was either equal to +1 or -1. Okay. Suppose it was +1, gamma L is equal to +1. Okay. Okay. If gamma L is equal to +1, so we will just mark this with some short form as VSWR, voltage standing wave ratio. Okay. So, I will have voltage standing wave ratio to be equal to 1 plus 1 divided by 1 minus 1, which is going to be infinity. Okay. The minimum voltage in my transmission line was 0, because of which my voltage standing wave ratio is infinity. So, I am having huge standing waves in my transmission line, that is what it means, right. If gamma L is equal to -1, this does not change, you will still have perfect standing waves in your transmission line. So, the difference between short circuit and open circuit is not easy to ascertain by just looking at VSWR, all right. So, you will be having the ratio between your Vmax to Vmin to be equal to infinity. So, if you measure a standing wave ratio to be infinity, that means that you have some extreme termination problems in your transmission line, maybe it is an open or a short circuit. Okay. But it is also quite possible that the load reflection coefficient is 0. If that is the case, we call this transmission line to be having a matched load at the other end of the transmission line. If the load is matched and the load reflection coefficient is 0, the standing wave ratio, okay, will become 1 plus 0 divided by 1 minus 0, that is equal to 1. So, the standing wave ratio in your transmission line is going to be equal to 1. Okay. So, the standing wave ratio goes between 1 and infinity. In the case of matched impedance, you will have standing wave ratio of 1. In the case of extreme terminations like open circuit and short circuit, your standing wave ratio will be infinity. Okay. Okay. And one could also think about what will happen to your maximum current. We now know that the maximum voltage standing wave ratio is telling you about the voltage. One could always use Ohm's law and try to find out what the maximum current would be. So, this would be say I max in your circuit could simply look like V max divided by Z naught, your transmission line, and I min would simply be V min divided by Z naught. This is just applying Ohm's law. So, this would be the maximum and the minimum currents in your transmission line. Okay. So, this gives rise to some thoughts. Okay. We have talked about the impedance measure from the input side. Okay. So, we had talked about the impedance in the transmission line looking from the input side, which is known as Zn. Okay. So, now we have to think about what Zn could look like, right. So, we can write down Zn min. What is the minimum impedance that you can measure? Okay. Which means that I will be having minimum voltage on the numerator divided by the maximum current in the denominator. Okay. And since I max is V max divided by Z naught, okay, I can substitute for I max and I will just get Z naught divided by VSWR. Now, if I know what my standing wave ratio is going to be, I can clearly calculate what the minimum input impedance could be, all right. It is going to be Z naught divided by VSWR. Now, you can notice that the VSWR goes from 1 to infinity. Okay. So, the minimum Zin that you will be measuring is Z naught, maximum is 0. Okay. Now, let us also look at what the maximum value of Zn is going to be. Okay. Zn max will be maximum voltage on the numerator divided by the minimum current at the denominator. Okay. I can always substitute for I min. I min is equal to V min divided by Z naught. Okay. So, this becomes VSWR times Z naught. This means that your maximum input impedance will go between 1 and infinity. Okay. I mean Z naught and infinity. Okay. Okay. So, these are the ways of looking at what your minimum impedance and maximum impedance in the transmission line can be, minimum current, maximum currents, what they can be. Usually they revolve around finding out the voltage standing wave ratio. These quantities are important because if you are dealing with transmission lines and if they have to carry some current, you want to make sure that electrically and mechanically it is going to be stable. You want to make sure that the current rating for the materials that you are using is going to be supporting this levels of current, all right. And when you are talking about impedances, you need to know the range of impedances. Unfortunately, for the open and short circuit, the impedances are not small, I mean the range is not small at all, right. You can go anywhere from 0 to infinity in the case of impedance that you are measuring from the input side. So, if you are going to measure the impedance of a transmission line from the input side, all these equations tell you is it could be anything. Okay. So, it is not easy to arrive at a conclusion just by measuring impedance on the source side. You need to have lot more additional information in order to figure out what is going on in the transmission line. The second thing that we should remember is during the design phase of the transmission line, we need to estimate what the standing wave ratios could be for the extreme termination cases, and then we have to figure out what the maximum current and the minimum current in your transmission line could be, maximum voltage and the minimum voltage should be. Then based on that you can design your insulation for your transmission line to support that voltage levels, and you can also make sure that the dissipation of the heat in your transmission line is taken care of when the maximum current is flowing without melting any part. Okay. So, from design point of view, calculation of VSWR is very important. From diagnosis point of view, VSWR can tell you what kind of load termination is present, whether it is an open circuit, short circuit or anything in between. It could tell you that. Okay. So, with that we will stop.